Thank you for the introduction. This is joint work with Mark Giesbrecht and Eric Schaust. Eric Schaust is my PhD advisor, and I will be talking about the bit complexity of some randomized algorithms in real algebraic geometry. There are two algorithms that I'm going to talk about. The first algorithm computes 1 point on each connected component of a smooth real algebraic set. We determine the bit complexity and the error probability. And in doing so, we develop some techniques that we are now reusing in the analysis of a second algorithm, which decides connectivity queries on smooth and bounded real hypersurfaces. This work is ongoing, but I will end the talk with some preliminary results. So for the first problem, let capital F denote a sequence of polynomials with n variables of length p, integer coefficients. Suppose that the polynomials define a radical ideal and a smooth variety that is equidimensional of dimension n minus p, and consider the problem of computing at least 1 point on each connected component of the real points of the variety. This is a basic but important subroutine in real and semi-algebraic geometry. It's used in many higher level algorithms. It's also useful on its own because we can decide if the algebraic set has real solutions, and we can determine an upper bound on the number of connected components. Our starting point is an algorithm by Safai, Eldon, and Schaust from 2003. The algorithm uses random changes of variables that are proven to generically ensure certain desirable geometric properties. By generic, I mean that there's a certain hypersurface that contains the bad parameter choices. There's a random choice that's made, and provided that it misses the hypersurface that contains the bad choices, then the geometric properties are established. The cost was given in an algebraic complexity model. We determine the bit complexity and the error probability, and we provide a quantitative analysis of the genericity properties, namely weak transversality and Noether normalization for polar varieties. By quantitative, what I mean is that we bound the degrees of the hypersurfaces that contain the bad parameter choices. And then we use the Schwartz-Zippel lemma to give precise probability statements for the success of the algorithm. And as I mentioned a bit in the introduction, the techniques are general in the sense that they would apply to algorithms in real algebraic geometry where weak transversality or Noether normalization for polar varieties are required geometric properties that are established by a random change of coordinates. And in particular, we are reusing the techniques now to analyze this other algorithm that decides connectivity queries on smooth and bounded real hypersurfaces, and I'll talk about that in the second part. The main result for the analysis of the first algorithm is the following. Like I said, let capital F denote this sequence of polynomials. Assume that the degrees are bound by D and the heights are bound by B. And we suppose that the polynomials define a radical ideal and a smooth and equidimensional variety of dimension n minus p. The height of a polynomial, which is a measure of the size of the coefficients. If there's integer coefficients, that's the maximum of the logarithms of the absolute values of the coefficients. For epsilon given between 0 and 1, we prove that there exists a randomized algorithm that takes f and epsilon as input and returns a finite set that includes at least 1 point on each connected component of the real points of the variety. The algorithm succeeds with probability at least 1 minus epsilon, and otherwise returns a proper set of the points, or fail. And in any case, the algorithm will use in SOFTO notation, which means that we ignore polylogarithmic terms, d to the power of 3n plus 2p plus 1, log 1 over epsilon, b plus log 1 over epsilon. Bit operations, the polynomials in the output have degree at most d to the n plus b, and height in SOFTO again, d to the n plus p plus 1, b plus log 1 over epsilon. The result is roughly optimal in the sense that it's equal to the output size times the algebraic complexity. It's also close to what is matching what is implemented in practice. in Maple available through the REG library, which stands for Real Algebraic Geometry. There's a different algorithm for this problem with bit complexity roughly d to the big O(n). This algorithm is much more general. There aren't assumptions on the input polynomials, but given the generality of this algorithm, the constant in the asymptotic notation is quite large, and to my understanding, it's not implemented in practice. To explain the algorithm, I first need to introduce polar varieties. Consider the Zariski tangent space to the variety at a point on the variety, and consider the canonical projection mapping, which takes points to the first I coordinates. The ith polar variety is the set of critical points of pi sub I on the variety. Consider the truncated Jacobian matrix of the input polynomial system where we remove the first I columns. Since we're assuming that the polynomials define a radical ideal, so for any point on the variety, the tangent space at that point is equal to the kernel of the Jacobian at that point, and therefore we can define the polar variety as the set of points where f vanishes and where the truncated Jacobian matrix is rank deficient. Therefore, we can define the variety by the vanishing of f and the maximal minors of the truncated Jacobian matrix. These equations they don't define a complete intersection, and that's actually a problem for us. I'll come back to that later. The hypersurface case is a special case where they do define a complete intersection. So for the hypersurface case, the ith polar variety is the vanishing of f and the partial derivatives and I plus 1 through n. Here I have a simple example of the second polar variety of a sphere. So f defines a sphere, and the second polar variety, which is the set of critical points of pi2 on the sphere, this projection mapping to x1 and x2, which is the red circle on the sphere. And the second definition that I gave is the second polar variety is the vanishing of f and the partial derivative of f and x3, which is the vanishing of f and x3. And again, that's pretty clear that that's the red circle on the sphere. As I mentioned, the downside to defining the polar variety using the minors of the truncated Jacobian matrix is that these equations in general don't define a complete intersection. Our solution is to use an alternative modeling of polar varieties that involves Lagrange systems. We introduce new indeterminates, L1 through LP, and define these Lagrange systems. So this we have this linear form at the end of the system there, and the point of that is to exclude the points where the L's are just identically where all of the L's are 0, and we have to choose we choose to use randomly, but they also have to be generic so that we don't exclude components of the polar variety. And then the system defines, so a solution to the system characterizes when the truncated Jacobian matrix is rank deficient, and therefore projections to the X space give the polar variety. Here's the same example again, but now with the Lagrangian modeling. And this is a really simple example. So there's just one new indeterminate, capital L. The truncated Jacobian matrix is just 2 times x3. The Lagrangian system is f L times x3 in a linear form L minus 1. This variety on the left-hand side is equal to the variety on the right-hand side because those equations are a lexigraphically ordered Grosvenor basis of the ideal defined by the polynomials on the left-hand side. And again, it's pretty clear that when we project to the X space, we get the second polar variety. Now that I've introduced polar varieties, I can give an overview of the algorithm. If we choose a generic change of coordinates A, then the input polynomial system is known to be, we apply a generic change of coordinates A to the input polynomial system. Then the ith polar variety is known to be equidimensional of dimension I-1 or empty, and to be in no other position. Then we choose a generic point sigma and solve these systems of equations defined by x1 minus sigma 1, followed through by xi minus 1 minus sigma I minus 1, then defining equations of the polar variety for I from 1 to n minus p plus 1. Geometrically, this is the intersection of the ith polar variety with the fiber of the projection. All of these systems, all of them have finitely many solutions, and their union will contain 1 point on each connected components of the real points of the variety. As I mentioned, we don't want to use the minors of the truncated Jacobian matrix, so instead we solve these Lagrangian systems and then compute the projection onto the X space. To summarize our contributions, we analyze precisely the conditions on the chain of coordinates that guarantee success. We revisit proofs given in some previous work and give quantitative versions of those results, where we bound the degrees of the hypersurfaces that we have to avoid. And to solve the equations in the main algorithm, we use an algorithm by Cephei, Eldon, and Schaus. There's a complete bit complexity analysis available for that algorithm. Several of the generic properties of polar varieties are consequences of weak transversality. Thom's weak transversality is a generalization of Sarge's lemma, which states that the set of critical values of a smooth function have measure 0. There's algebraic versions which show that the critical values are contained in algebraic sets in the codomain. We develop a quantitative version which allows us to bound the degrees of the hypersurfaces that we have to avoid. And in our context, the bad parameters show up as the critical values of a smooth function. So let n, s, and m be integers with m less than or equal to n, and let phi be a polynomial mapping with domain Cn cross Cs and codomain Cn. For a point theta in Cs, let phi theta be the induced mapping that takes points x to phi of x theta. A point z is a regular value of phi if and only if for all y theta with phi y theta equal to z. The Jacobian of phi has full rank at y theta. We prove the following proposition. Suppose that 0 is a regular value of phi, then there exists a non-zero polynomial gamma of degree at most d of the m plus n, such that for theta and Cs, if theta does not cancel gamma, then 0 is a regular value of the induced mapping phi theta. And here, our contribution is the degree estimate. I have another example. This example is meant to illustrate the proposition, and also it's meant to illustrate how we use the proposition when solving the equations in the main algorithm. Let f be a square root polynomial, degree at most d, defining a smooth variety, and let phi be a polynomial mapping defined by the polynomials x1 minus theta and f. Notice that the Jacobian of phi has full rank 2 at any point that cancels equations at any point in phi inverse of 0, because the partial derivatives of f and x1 and x2 can't both simultaneously vanish, and therefore the assumptions of the proposition apply. Therefore, a polynomial gamma exists with degree at most d to the power 4, such that when theta does not cancel gamma, then 0 is a regular value of the induced mapping. And therefore, the Jacobian of the induced mapping is full rank 2 at any point that cancels equations. By the Jacobian criterion, then the ideal of x1 minus theta and f is radical. And this is true for all theta, all complex numbers theta, except at most d to the 4 values. The whole point of this example is to illustrate how we use the proposition when solving the equations in the main algorithm. So compare the polynomial mapping in the example with the equations that we solved in the main algorithm. By following the same steps as in the example, we found the degree of a polynomial such that when sigma does not cancel that polynomial, then the equations we solve in the main algorithm have finitely many solutions. This part of my talk is a little bit tedious, but please just bear with me. We say that F satisfies HI if the ith polar variety is either empty or I-1 equidimensional, that the Jacobian matrix of the polynomial is defined by F and the Lagrange equations has full rank at any point that cancels equations, and that the ith polar variety is either empty or in another position for pi sub I-1. Notice that I don't have the linear form with the Lagrange equations this time, and that's because we have to choose the coefficients of it so that they are generic, and that will come. I'll explain that in a moment. Recall that an algebraic set X is in another position for the projection pi d. An algebraic set of dimension d is in another position for the projection pi sub d when there is an integral extension. When this extension is an integral extension, it's a consequence of another position that if you take a point in the target space, then fibers will have dimension 0, so that they are finite and not empty. For instance, the algebraic set on the bottom left is another position for pi 1, but the algebraic set on the right is not in another position for pi 1. Here I have a comment written in red at the bottom, and that's note that if we apply the change of coordinates to the input polynomial system F, then what we obtain may not be equal to applying the change of coordinates to the polar variety itself. So consider that the variety of F is a line, but not a vertical line. To say that when you apply the change of coordinates, it becomes a vertical line. And then the first polar variety is infinite because every point is a critical point. But if you apply the change of coordinates at the end, then the first polar variety of a line that's not vertical is empty, and applying the change of coordinates to the empty set gets back the empty set. We say that F and sigma satisfy HI prime if 0 is a regular value of this system of polynomials, and the open set defined by having L not equal to 0. If F, this is assuming that F satisfies HI. And here, if we assume that F satisfies HI and F and sigma satisfy HI prime, then we say that U satisfies HI prime prime if U is such that the projections on the X space of the solutions of 1 are the solutions of 2. We prove that there exists a polynomial delta 1 of degree at most 5n cubed, 2d to the power of 5n, such that if A does not cancel delta 1, then A is invertible and FA satisfies HI. Assuming that F satisfies HI, we prove that there exists a polynomial delta 2 of degree at most n d to the power of 4n, such that if sigma does not cancel delta 2, then F and sigma satisfy HI prime.
Excuse me, just I don't understand exactly what you mean that if sigma does not cancel something, so
if it's not a 0.
Modulo.
Not modular, just so in this case, let me know if I'm answering your question. Like delta 2, there are I minus 1 indeterminates. So if sigma if sigma makes this polynomial 0.
Just 0. Okay, sorry, I misunderstood. Okay.
And assuming that F satisfies HI and assuming that F and sigma satisfy HI prime, we prove that there exists a polynomial delta 3 of degree at most n d minus 1 to the power of n, with the property that if U does not cancel delta 3, then U satisfies HI prime prime. So the algorithm first randomly chooses the change of coordinates A, And the entries of A are chosen from a set sufficiently large so that the probability that A cancels delta 1 is at most 1 minus epsilon, which we can do because we know the degree bound for delta 1, and we can use the Schwarzschild lemma. The algorithm next randomly chooses sigma. In the same way, we quantify again using the Schwarzschild lemma, bounding the probability that sigma cancels delta 2 to be less than or equal to 1 minus epsilon. And then finally, the algorithm chooses U at random, and we quantify again using the Schwarzschild lemma and bound the probability that U cancels delta 3 to be less than or equal to 1 minus epsilon. So we call the second algorithm, which decides. Recall that I mentioned that there are two algorithms, and the second algorithm decides connectivity queries on smooth and bounded real hypersurfaces. It does this by computing something called a roadmap. A roadmap for an algebraic set X is a curve with non-empty and connected intersection with all connected components of X. Roadmaps decide connectivity queries and have applications in robot motion planning. Consider the following problem. Let F be a square-free polynomial with rational coefficients such that the variety of F has a finite number of singular points and the real points are bounded. Compute a roadmap of the real points of the variety. Our starting point again is another algorithm by Safei, Eldon, and Schaust. The algorithm also uses random changes of variables that are proven to generically ensure weak transversality in another position. The algorithm is recursive and based on calculating polar curves of polar varieties. And the cost again was given in an algebraic complexity model. So we are determining the bit complexity and the error probability and giving a quantitative analysis of the genericity properties. We're using the techniques from the analysis of the first algorithm. We're giving quantitative weak transversality and other position statements. There are some additional genericity properties that we need to give quantitative versions of. And one of the more difficult properties is the following. Suppose again that capital F denotes a sequence of polynomials. Assume that the degrees are bound by D. Assume that the polynomials define a radical ideal and an equidimensional variety of dimension n minus p with a finite number of singular points such that the real points are bounded. We say that F satisfies GI if the first polar variety of the ith polar variety is finite. This has been proven to hold generically, and we give a quantitative version. So again, we prove that there exists a hypersurface or a polynomial with degree at most n p plus n to the power of n 2d to the power of p plus n with the property that when A doesn't cancel delta, then FA satisfies GI. Briefly, I will mention some other work, other algorithms on computing roadmaps. John Kenny introduced the roadmap. I think it was 1987 or it might have been 1988. It was the first algorithm that solved connectivity problems and complexity singly exponential in the number of variables. He gave a deterministic algorithm where the exponent in the complexity is n to the power of 4, and a randomized algorithm with the exponent n squared. And since this time, there's been a lot of work on lowering the exponent in the complexity. Soon after, there was a deterministic algorithm with complexity n squared. The bullet in red is the algorithm that we are analyzing. Notice that it's far less general, but shortly after there was a deterministic version for general algebraic sets. And again, since this time, there's been a lot of great work on lowering the complexity and removing assumptions. The algebraic complexity and the degree of the output, it's ND to the power of n to the 1.5, and we expect the height to be the same. if we use the classical arithmetic Bézier theorem, this doesn't work. We get n squared. So arithmetic Bézier is like Bézier, but rather than getting a degree bound, you get a height bound. The problem is that the equations that we need to solve have a very special shape. There are two blocks of variables, and the blocks of variables are subject to different constraints. One block has high degree in bit size, the other block has low degree in bit size. So classical arithmetic Bézier does not distinguish the two blocks, and it overshoots the complexity estimate. Our solution is to use multi-projective height techniques that involve something called the arithmetic Chow ring, which I'm not going to say anything about what that is, but it's a tool that precisely allows you to handle the two blocks separately. And when we use it, we get n to the 1.5, which is what we want and expect. That's the end. Thank you.
We have any question? Okay. I don't understand precisely when you talk about the probability, you have that the good output. So you take random change of variables. So I don't understand what's the measure probability used on the change of variables. Like when does you choices or like all the change of variables possible? Or
So we use the degree bound. So say we're doing the change of variables, the A, then let me know if I'm answering your question. We choose the entries of A from a set, but we make the set in terms of the degree bound of that, the polynomial that we want to avoid, the hypersurface that we want to avoid. We use that degree bound in determining the size of that set.
yes, but the measure probability you use for giving your probability statement is on all the possible change of variables.
I'm not sure what you mean. So it's just the degree divided by like the size of the set, I think is what we do.
Yeah, but like it's infinite. The change of variables.
I'm not. What do you mean it's infinite? Is it
the change of variables on the C2D you use? Yeah, it's all the invertible matrices.
So we have the matrix is the entries of the matrix come from a finite set.
Okay. Are they integers?
They're integers, yeah.
Yeah, but bounded.
What? Sorry?
Bounded integers.
Yeah, like so, I feel like I'm not understanding the question. Like we choose a set, and the size of the set is determined by the degree of the hypersurface, and epsilon, and then we take the entries from that set and make the matrix. But the number of matrices is finite.
Okay.
Is that answering your question?
Yeah, yeah.
Okay.
So, okay.
Maybe I should have made that a bit more clear.
Yeah, we can discuss it later.
Okay.
Thank you.